everybody hear me? So a couple of things. I sent everybody an email about TabHat. And I spoke, there were a number of students who came, especially from this section. And they said that they connected to TabHat and then they submitted their answers, but they got a 0. And I was surprised because they said that they were trying up until the end of, the beginning of the class. And usually, as I will do right now, I would get on this, which is 502. Okay, that's not exactly. So I would get, for example, on this, and then I have to go back again. And then I will go here, which is this. This is 502. And as you see the exercises, I see the red. That means that one of these exercises has been assigned. All right, and then I unassign it. And then I assign it as a review. So you can see it. You can see the exercise. So usually I do it like 2 or 3 minutes before the lecture. And then in any case, I had a lot of students who said that they submitted their answers, but they did not get any points. And I called TabHat. They said the only, well, first of all, and I created a student account so I could see it myself what they were telling me. So it is true, I created a student account for this class, for this exercise, and I submitted my answer and I got a response that my submission was successful. If you don't get a response that your submission is successful, you have not submitted anything, number 1. Number 2, if you have submitted something, you think, but you have not received a response that your submission is successful, so there is a problem, try again. Maybe your connection on your end, on their end, I don't know where, did not go through. If you have a problem for 5 minutes, like continuously, or you have tried a couple of times and then it has not been corrected, then you have to email me at that point in time. Not later, not 2 days later when you don't remember when you tried to submit and I cannot figure out when you tried to submit. So to avoid those misunderstandings, please make sure that you don't submit when it is in review. You don't submit after the time I have given you because I will unsubmit. And when I unsubmit, you cannot submit an unassigned, I should say, you cannot submit an answer. So obviously, if you try to do it later, you're not going to be able to submit anything. You're going to get 0. So for the future, I don't know what the problem was. Obviously, I cannot speak to the conditions under which a number of you had that problem. I am going to have a makeup assignment for cases like this, where either on TabHat or something else, that you missed points, not points, you got lower points than you wanted, but you missed points. You missed points because you could not participate, all right? We are going to have a makeup assignment, which is going to happen, as I think I've said many times, after the midterm. And as we approach March, I will tell you, I will send a note to everybody, say, tell me whether you have missed points and why. Because a lot of students think that I missed points because I did not get the maximum. These are not what I call missed points. Missed points are those that you missed participation, all right? And I will collect those responses and I will know how many points people, and I will create a makeup assignment to accommodate everyone. So that's what you have to keep in mind. Also, this weekend I'm going to write the solutions for all of the TabHat exercises. So you have the final solution. You don't know why your answer was not correct. So I will post rather the solutions to those. Any other questions about that issue? Okay. Having said that, so today I'm going to assign at the end a quiz for Monday. So let us now go to the lecture today, and to remember that last time on Wednesday, we started talking about a perfect conductor and what happens to the electric field, what happens to electrons in a perfect conductor, right? That what happens when you have conductivity. It might not be a perfect conductor, but it may be a conducting material. Whenever you have conductivity that we show by sigma, the Greek sigma, let me, just a second. Wait, put something in there so I can write. I hope that I have also and to write, otherwise, okay. Well, I will not write everything is in there, but I will try to show you. I don't know how. All right, I don't have my pen here. I don't seem to. Oh, there it is. Sorry. I got so confused right on. Okay, here's the pen. I'm good. And thank you for giving me. All right, so here, what we said, the sigma. All right, you see sigma is the conductivity. And do you know in what we measure conductivity? One over ohm per material, per volume, for example. All right. And why is that is 1 over ohm? How do you remember it? You will see it later from the current is equal to sigma times the electric field. Electric field is measured in volume per meter, all right? And so sigma, because current measured in amps, so sigma has to have for that particular application, if J is a total, is not a current density, all right? So for that application, sigma is going to be measured in 1 over ohm divided by, I mean, it's like ohm minus 1 per unit length or unit area, depending on whether you have the densities. We will see that in detail later. I'm not going into this now, but your conductivity is a measure, or Siemens, you know, as somebody mentioned. Conductivity is a measure of how much or how fast or how many charges, electrons particularly, can move through the material. All right, if the movement is easy, there will be many electrons. So the higher the sigma, the easier the movement of free electrons. So we'll have more of those free electrons moving, which means that we are going to have more of that, what we call conducting current. When sigma goes to infinity, then practically all of the electrons move. And what happens, as you show here, if the electrons move, usually if there is nothing around the material is going to be in equilibrium if there is no other fields, all right? Which means, yeah, there will be no reason for the electrons to move, because usually they move under the influence of an electric field, or because there has been some disruption in the energy levels and so forth. Usually disruption in energy levels comes from temperature. So if you take a conductor and then you warm it up in someplace. So what happens, you agitate the electrons a lot because the thermal energy changes into electric energy. You agitate the electrons and then they split, they leave the atoms and then they move around a little bit there. Of course, at the end, because their movement is random, there is no a particular current that goes into any particular direction. So yes, there is a lot of activity of electrons, but it's temporary for as long as the effect applies and does not give any particular current. However, when you have a particular electric field that is exerted, is created by a source, in this particular case is a charge, is a point charge, then what happens to these electrons is that there are two things that happens to them. And I will, first of all, do the following. I will take this one, all right, and I will cut it for the time being. If I cut this, that shows what happens to a point charge when it is by itself. Usually, when a point charge is by itself, what kind of electric field is excited? It goes out like this. All right, we've seen that. And the electric field goes out as 1 over the distance square from the point charge. Okay, so now what I do, I bring next to this charge or close to it, a conductor. So when I bring this conductor, put it here, paste, all right? What happens is that those lines that were going straight, and it was this one and this one, and I will leave this one there. The ones that they were going straight have now changed their direction, have changed their shape, or the electric field has changed the direction for the following reason. So when you have a positive charge, and then you have a perfect conductor, which means that the free electrons can go wherever they want, because there is a charge, the electrons are feeling the attractive force, all right, that is exerted on them from the charge, which is positive. So under the influence of that force, and because they don't have mass, they don't have inertia and so forth, they are going to move as fast as possible to the closest physically possible location to the charge, all right? Now, the shortest distance from the charge is this one here. Let me do it with a different color. Is this one. Okay, that's the shortest possible distance from the charge. And therefore, the first electrons that will be the closest to the surface will go right there. And then other electrons will follow. But what happens? The electrons not only feel the attractive force from the positive charge, then they start having repulsive forces among themselves because they have the same charge. So the electrons cannot get too crowded. They will have to balance the repulsive forces among each other with the attractive force from the positive charge. And therefore, you see this kind of distribution. More electrons, not on top of each other, but more electrons distributed exactly close to the shortest distance. And then as you go further away, you have the electrons to be distributed further apart. Okay, so that's what happened with electrons. Then what happens when the electrons move? Okay, so let me erase this now. And then let's assume that the electrons moved and they left behind them different empty seats, like holes, All right, so this is one, will be everywhere. As long as you leave a hole behind it. Okay, the question is what's gonna happen to those holes? All right, and then you have many others. So here, and so forth. What happens to them? There are electrons below them because you remember this is an infinite long ground. So the electrons that are further down, they will start filling up the holes, all right? Because all of the electrons fill the attractive forces. And either they're gonna move up, or if there is too much crowding there, they're gonna fill these holes. They're gonna go places. They're not gonna be in the middle doing nothing, all right? They have eventually, this whole thing eventually has to go into equilibrium by itself. I mean, equilibrium meaning all of the forces have to balance out. So all of these holes will disappear, all right? And as a matter of fact, what happens when an electron, say if I have an electron coming from down here, and then goes and fills this hole, what happens? It leaves a hole behind, all right? So practically, this hole here is going to disappear, this one, and practically it's gonna happen, what is gonna happen is gonna come into that position. So all of the holes eventually will start traveling down, deeper into the conductor, until all of this, they will travel down until they disappear, all right? Until they go so far away that we don't care anymore about them. So this is gonna try to go to what we say theoretically infinity. So they go really away from the space of interest, all right, that we are studying. So practically when all of these holes leave and then we don't see them anymore, so what's happening here? The rest of the material in our region has no charges. So when everything stabilizes, the material inside has no charges. And all of the field lines from the positive charge are stopping at the electrons. So then what? Here is gonna be a zero electric field, all right? There is no electric field inside a perfect conductor. Okay, any questions about this? Let's assume now that we don't have a perfect conductor, which is like a half space, but we have a conducting slab, like a piece of metal, for example, that is thin, but then it's planar, extends to infinity on both sides, all right? So what happens here? Again, we bring this positive charge. In this particular case, first of all, we have to get rid of this. In this particular case, still the electrons, when they feel the attractive forces from the charge, they are gonna go and occupy the upper surface. And then the remaining holes are gonna go, because all of the, any holes in between are gonna be occupied with the excess electrons, the other electrons, and then eventually all of the holes will go at the bottom. But here's what happens now. The top is negative charges, the electrons have two, they have practically the following forces to balance. The attractive force from the charge with the repulsive forces from other electrons around them. All right, so eventually they stop in whatever they crowd as much as they can, close to the closest distance from the charge, and then they distribute out, gradually. The holes have which forces to balance out? Only the repulsive forces. The holes have only the repulsive forces, so they distribute themselves evenly. So that's the interesting thing you need to keep in mind, because that is going to apply into other problems, as you will see. So all of the negative ones that see the charge on the other side, they will crowd into places, into especially the place that's closest to the charge. And then the positive holes that have gone on the other side will just even out. Okay, What happens when you have positive holes right there? They have balanced themselves out, all right? But they are positive charges that are distributed on the lower surface of the conductor. So then what do positive charges do when you distribute them on the surface of a conductor? They radiate an electrostatic field. And because now all of these will be on an infinite planar surface, uniformly distributed, what kind of a field are they going to create? We solved that problem, remember? Constant. So the field that you are going to see underneath it is going to go like that, and it's going to be a very strong field. All right? It's not going to go down with distance. Now, of course, that's not a good idea here because I had a charge, I brought the charge close to the conductor. I mean, this is part of my problem. And usually we put charges, meaning lines that carry charges, or antennas, for example. If we are to bring them close to the conductor, we do that because we want the conductor to provide some kind of a shield. We want the conductor to stop the radiation from going to the other side. But this way, we don't stop the radiation, we make it worse. So then what do? Then we ground the conductor, especially that other side of the conductor. We put a ground here. We connect it to the ground, which is an infinite source of negative charges. And then what happens? The electrons will flow from the ground up here, will start flowing up, and they will come here. All right, electrons will flow close to the surface, of course, all right? And they will neutralize all of the positive charges. So then what happens in this case? Then all of the charges will disappear from the lower surface. So with this one, I'll put there. All of these charges disappear, all right? There. And all of this. And of course, you have the same conductor here. The upper charges, they stay where they are. And just the lower charges have gone. They got neutralized. So in this case, if there are no charges underneath it, what happens to the electric field at the lower side? Goes away. And that's how, what we have to do to be able to stop the field from penetrating through. Even if there is no field inside the conductor, the charges that accumulate on the other surface create a radiated field. They radiate that field. So we ground it a lot of times when we have conductors inside the extends, in fact, large surfaces, as you have seen in some of the pictures of the circuits that I showed you, then you try to ground them. So you make sure that whatever charges have been concentrating right there, they all get neutralized, all right? Otherwise, you're gonna have so much crosstalk. What is crosstalk? When fields see each other, all right? When charges see each other. What happens when one charge sees another charge, the whole field distribution changes. All right, so whatever happens, the total field is of the original charge is impacted by the field of the other charge. And then in cases like this, you have a field that is what we call parasitic because we did not design for it. So you have a lot of parasitic effects when you don't have good grounds in your circuits. Okay, so that is shows that here. That is here. So what I wanted now to show you, those notes have been on Canvas. What I want to show you is the same thinking applies when instead of a planar conductor, you have a conducting sphere. And before the sphere was introduced, we had a Q somewhere very long distance. So for example, let's assume that I am a charge here and I radiate everywhere uniformly. But then I have an observer, which is down there at the farthest corner. And then the observer has a equipment that measures the radiated field. Now the observer, my size going down there, will be able to only measure the field of a surface that practically, because the person is so far away, is gonna only correspond to a few degrees from me, all right? I mean, that surface is like, it's gonna be a narrow angle that is created between me, that I'm the source, and that little surface. Now, when that happens, and it's only a few degrees, practically what I observe is like a field that comes planar, like that the lines are parallel. All right, that's what it is. That's what I see. I don't see this narrow angle disappears for me, and then it looks like the field has the same value on every point of the surface that I'm measuring, and then has the same direction. Okay, so practically, if you have a charge in a very large distance from your measurement area, and let's assume that it's a positive charge, as I will show here, without anything, the electric field around the observer is going to look like this. Okay. Now the charge, granted, is very far away, but the electric field that I will see is going to look like parallel and constant in that place. And because I said, also the radius is so far that even if I measure it in a small volume still, it will seem like the field depends on the distance between me and the source, and it's the same for every point in the volume I'm measuring. So it looks like that. It looks like a uniform field that is parallel also. What happens if I put a sphere in there? The moment you put a sphere on the left, first of all, because of the charge, which is plus Q, all of the electrons in the sphere will try to come as close to the charge that created that field as possible. So they will all try to crowd on the front side. And because at that point, will I say crowd, but because the field lines come parallel, they're not going to be as crowded as you see them when the charge is very close, all right? So they're going to all come to the side of the charge that creates the field. And for that reason, all of the holes will go on the other side. And therefore, what happens is you have that deformation, as we call it, of the field because of the sphere. That is important for radiating problems, all right? If you have an antenna, so your charge is the antenna, for example, and that creates a field, then the field that the antenna will create in open space, it is deformed by whatever conducting surfaces you have. What does that mean? Conducting surface could be the frame, for example, of a large building. If I have an antenna, let's assume that this is not only brick, but it has usually buildings like that that do have metallic frames, all right? So this building to an antenna that is far away, a communications antenna from a tower, it looks like a conducting structure. What happens when then I design this antenna to send a field to many users? Then the buildings change the field locally. And if the buildings are one very close to the other, then you have a total change of the field that you are supposed to have. So what happens? In most cases, you are not going to have a good reception. And that's why when you go to downtown areas where there are buildings very close to each other, these buildings really alter because they are conducting structures, all right, they alter their field distribution, which is so important for users to have reception. And that's why without repeaters, without devices that receive the field somewhere, they amplify it and then resend it, which we call repeaters, you're not going to be able to have any mobile service, all right? So that is what happens, and that's why it is important to know how different structures, of course, a symmetric, a metal sphere that is so symmetric and have that kind of symmetry, spherical symmetry, is a very fundamental structure. In reality, when you start thinking about that problem, people employ more complex structures. And of course, there are methodologies to do that. But the bottom line is the whole problem is because of this, all right? The issues that we face. Okay, now here you have another problem. Let's assume you have an antenna in the middle of different structures. Let's assume buildings. Well, one building is like those assume that they are very tall. We look only at cross section at this point. The one building is like a rectangular tower. The other has a different shape. What that shows you here is that the field is gonna be concentrated around the antenna because of these other conducting surfaces, conducting bodies. And it's going to be mostly there, and outside there will be regions that we will consider to be blind spots, all right? And usually what happens here, this is more to show you that when you have an antenna, a charge, positive in that case, all of the electrons will come to face the charge. And if you have sharp areas like here, the electrons will mostly concentrate there. They like the sharp edges. And they will be more smooth in the other areas. Of course, the holes will have a similar kind of behavior, but they're going to be on the other side, all right? And then you create that field, these kinds of fields, which you can have a field here, for example, the field there in this particular location. Well, let me see this. If you are a person who receives there, your reception is going to be extremely weak, all right? The same thing for a person down here, for example, compared to what you would normally have without this. So in any case, so that is to show you what happens. This is not only true for antennas and in areas that you have these kinds of conducting structures. This is also very important to know in circuit design on what is going to happen when you bring close to your line different conductors, all right? How the fields are going to deform to really create what we call crosstalk. And that is why we are studying. Okay, so here we are going to see now what happens when we have a, let me stop before we go here. Any questions so far? Okay, so now we are going next step. We have a sphere instead of a planar conductor, and we have a charge inside the sphere, all right? And the sphere has thickness. Okay, what happens? Again, the same kind of thinking. There is a charge and it's not at the center, so it is located asymmetric in general. There is some kind of symmetry along one axis, but not spherical symmetry. Okay, so then the charge in the particular case is negative. So what is going to happen? All of the electrons, because the electrons move, the holes is the lack of an electron, if you like, all right? But physically, the electrons move. So all of the electrons, because the charge is negative, they're going to feel how many forces? Well, two types of forces. A repulsive force because of the negative charge, and repulsive forces among themselves. So they will have to move away from this charge the red one, which is negative, as much as possible. All right? And then, because they do that, the electrons, then they leave behind them holes. And all of the holes will concentrate in a way that they are the closest to the negative charge. All right? And why is that? Why do you think you're going to have more of the holes in close to the negative charge? Because more of the electrons will have to leave from there. There's going to be a total depletion of electrons, all right? That's what happens from that point, because the repulsive force is going to be so strong. So practically, you have more empty, if you like, places, right? Very close to the negative charge. And then those even out as you go away. So you see, we indicate a lack of an electron with a positive charge, and you have more positive charges there, and then they go away. What happens to the electrons now that they have moved as far as they could? So they went to the outside of the conductor, right? They went there. The moment the electrons go to the outside and the field inside the conductor is zero, they have no idea what happens to the positive charges, to the holes. It's like they are living in a different world. So then the only thing that they have to balance, the only forces, are the repulsive forces among themselves. And what happens? That forces them to distribute themselves evenly on the outer surface. All right? So while inside the conductor, the holes do not distribute evenly, but they crowd very close to the negative charge. Outside, you have a different distribution, which means that the field lines inside and outside will be different. And the interesting thing is that outside, the field, if I am an observer from the in the outside of the sphere, I will feel a field as if the negative charge was at the center. All right? If I make measurements from outside, I will not realize that the negative charge was someplace else. All right? I will think that somewhere in the center. That's the interesting thing. Okay.
Why is that?
Why is that? Because I told you.
Able to tell since they're grouping up
the electrons do not see what the holes are doing. You know how it is? It's like you have a team of blue shirts and red shirts. And then you say, you know, I'm going to divide you. All of the white shirts go blue shirts. All the blue shirts go into this other room behind us. And then all the red ones stay here. Okay. Do you know what they're doing in there? They may have a party. We have no idea. Here we may choose to study as we should. There they may choose to party. That is possible. If somebody sees them, they will think that we both party. If somebody sees us here, they will think we both study. That's what happens really in this particular case. The electrons go evenly out because they only balance the repulsive forces among themselves, and that makes them even out. And then from the outside, I see that, and you know, I assume that the measurements tell me that the charge is in the middle. Okay. Now, we don't want the field outside, obviously, because usually we put conductors around charges or sources when we want to isolate the sources. So what we do in this case is in the other one. We ground the outside conductor. As a matter of fact, the outside of the conductor, not just the conductor, the outside of the conductor. That's extremely important. You ground the outside of the conductor, and then all of the negative electrons are going to float to the ground. Why is that? Why the electrons are going to go into the sea of electrons? Because in the sea of electrons, there is equilibrium. There is no energy disturbance. You know, the electrons live in peace. Nobody bothers them, if you could say that. But in any case, when you are an electron on a ungrounded conductor, you are at a higher potential than the potential of the electrons in the ground, which is 0 for us, all right? And therefore, from the higher potential or a higher energy level, you tend to always for equilibrium. You go to the lowest possible energy level. Is that right? That's what happens in equilibrium. So all of the electrons from the higher energy levels will fall into the lower energy, which means they will deplete. All of the electrons will leave the outside surface. And therefore, you're gonna have 0 field outside. All right? All right, in this particular case, in fact, what you will see is that I calculate the fields. And with what we've known, with Gauss's law, all right? So in this particular case, I use Gauss's law for inside and outside. All right, so I assume that the conductor has a thickness T or Greek T, and or Greek tau, whatever we call it, and that the outside radius R prime is equal to the inside radius plus the thickness of the conductor, all right? And then I'm going inside, and inside I apply Gauss's law to find the electric flux density. Here, we've done this before, so I'm not gonna redo it again. We have seen how to do this. And therefore, since there is only, I put a volume around the charge, then the volume integral of the divergence of D is gonna give us that charge Q. And therefore, since there is, the charge is at the center, and then I have spherical symmetry, I can then simplify my integration. So practically what I find here is that, in fact, here I will have to put a small r, just a second, because I think that. So a small r, which of course, when you go to the surface, to the inside surface, the field there is gonna be the value where r equals to capital R, all right? The radius therefore equals to capital R. Okay, so that's what we find for the inside. Therefore, from the inside, it starts from a very, very high value because R goes to 0, and R is the distance from the charge. And then it starts going down as R squared. And then I hit the conductor. The lines go vertically to the conductor. Then I hit the conductor, there is nothing inside the conductor. So the field inside the conductor is 0. And then I'm going to the outside region of the conductor. And the only thing that I see outside of the conductor is a uniform charge, which for this case is a uniform positive charge. And therefore I apply also Gauss's law here. And in this particular case, I find a volume that encloses the whole outside surface of the conductor. And then since I'm integrating volume integral on that volume, which is like the surface of a sphere that encloses the whole thing, then practically what I'm gonna find is the total charge there is Q, even if it's distributed on the surface of this sphere. See, all of this is Q. All right, it's nothing different, just Q but distributed. The same thing with the electrons inside. All of the electron charge is negative Q. And all of the holes have a total charge which is a positive Q. But the Q equal to the Q, which is at the center of the sphere. So then if I follow that, I find this expression where R is the distance from the center of the sphere. So here is what I see. This is interesting, isn't it? It's like what I see as a field is exactly what I would have seen as if the sphere was not there, like one point charge, and the field will go down as 1/r squared. And wherever the sphere is, I see 0. So it has not helped me, all right? I made the field 0 only where the conductor was, the outside, and then everywhere else it has remained the same. This is very interesting to see. Now, however, when I connect the outside of that conductor with the ground, then all of the electrons from the ground will flow and get their place within the holes, and then neutralize all the holes, all right? And then in that case, not only the field inside the conductor is 0, but the field outside. So if I could get this one here exactly the way it is. I could copy it, come here and place it, make it smaller. And then the only difference here is I will take this out, and the field from that point on is going to be just 0. And that's how it looks for a shielded conductor that encloses a charge. All right, so that's why shielding is so important. Next time, we're going to start with capacitors. All right, and we're going to talk about that concept. Now, I am I'm going to assign, close that, go to quizzes, quiz 4. Okay, quiz 4. What am I doing? Okay, this is the problem. You have to find which of these cases is the correct one. Similar to what we said today, all right? And I will assign it now, and you have until Monday. If you want to solve that, look at just the lecture today, okay? And I will assign it until Monday morning. Any questions? Okay, thank you.
So for this one, why don't these electrons like right here notice that there's more?
They don't
photons?
see them.
They can't feel the field, like feel the
Yes,
force.
they don't see anything. There is nothing in between. It's like a